Hello all, and welcome to the Resonance Science Foundation Unified Science Review. Thank you all for joining. Looks like we've got a good group assembled here, and I'm excited to share some of the latest discoveries, experiments, and advancements in unified physics and unified science. Today, we're going to be reviewing some really important information and experiments to understand that form a foundational understanding for unified physics. In particular, understanding the nature of the quantum vacuum. The ubiquitous energy of space. So we're going to be looking at the theory behind quantum vacuum energy or zero-point energy, as well as experiments that are directly working with that substantive energetic medium of space. So it looks like we've got most people joined in, so we'll get started with the review. So the two key experiments that we're going to be looking at today, reviewing today, is vacuum polarization and the quantum energy teleportation protocol. This is harnessing the quantum vacuum energy density and harnessing the intrinsic entanglement of the quantum vacuum. What is actually called literally entanglement harvesting or entanglement farming, using the infinite amount of quantum entanglement of the vacuum state to entangle quantum systems and to even teleport energy between them. So we'll be looking at some of the theory behind the development and emergence of the idea of the quantum vacuum. And so, there's good theoretical development of why it is believed that there should be a constitutive, ever-present energetic fluctuation in all of space. That's understanding the quantum vacuum. But then we'll look at experiments that are demonstrably showing that it's not just theory, that indeed there are constitutive, ever-present energetic fluctuations at the 0-point level. At what should be the level of zero energy, there is a continual energy flux. Then introduction to the idea of the intrinsic entanglement of that energy density, and an experiment recently performed that has demonstrated that intrinsic entanglement of the vacuum energy density and how to leverage that spatial correlation to teleport energy between two quantum systems. And then implications and applications of these ideas. Okay, so experiment recently performed that has produced particles from the quantum vacuum. This is okay. So The first experiment that we will review has to do with a process referred to as vacuum polarization, described via the Schwinger effect. This is a vitally important process to understand for the theoretical basis and applied engineering of technologies that can harness the energy of the quantum vacuum. Because one of the key processes in tapping the 0-point energy density is generating a gradient, i.e. polarization, in the vacuum energy fluctuations. This experiment is a demonstration of how mass energy can be extracted from the vacuum. And so there can no longer be any doubts about the possibility, that is, it's no longer theoretical, that technological engineering can extract mass energy from the vacuum. It is also important to note that we are looking at what we are looking at in this experiment is black hole physics of particle creation. Black hole physics are being mimicked in a tabletop experiment, in this case, utilizing graphene. And the experiment is verifying a long-standing prediction of using the electric field to generate particles from the quantum vacuum. That's known as the Schwinger effect. The Schwinger effect is producing particles from the quantum vacuum via vacuum polarization by generating an extremely large electrical field that generates a gradient in the vacuum structure. From a certain perspective, this is what Nassim has been doing for 30 years. Reverse engineering black hole physics to describe how we can potentially mimic those dynamics to produce limitless clean energy, gravitational control, and even wormhole travel. Those are all potential technological applications that come from the ability to engineer space-time. One of the ways that you engineer space-time technologically is via vacuum polarization. And we'll see how this has recently been done. So first, a review of the idea of quantum vacuum fluctuations. It's really important that we're all on the same page about this idea, because one of the things that I think one of the mistakes that we often make at the Resident Science Foundation, our scientists, research team, is assuming that other scientists and even non-technical persons will know about the quantum vacuum fluctuations. And actually, what I've come to find is that this is not necessarily the case. Even physicists, who should ostensibly have a very well understanding of quantum vacuum fluctuations, seem to not be entirely up to speed on what we're talking about with this idea. Quantum vacuum fluctuations are also known as the 0-point energy density of the vacuum. So there's a hypothetical state of space referred to in physics as the vacuum state. And the idea of the vacuum is a completely empty space devoid of any matter, energy, or forces. This state is hypothetical because it does not exist anywhere in nature. The reason for this is that the very fabric of the universe, space itself, is a substantive medium, a veritable limitless sea of energy. And this indelible and substantive field is the source energy for all matter and forces in the universe. So there is no such thing as empty space. A true vacuum is a purely hypothetical state. Nothing does not exist. So in quantum mechanics, you have quanta, which are little discrete wave particle packets. And indeed, when mass energy quanta are discussed, they are often conceptualized and referred to in terms of being particles, even though we should know better. Elementary quanta are still often viewed as like little solid billiard ball-like particles. However, a more accurate and precise description of quanta is described them not as wave particles or particle-like, but as energetic excitations or oscillations of fields, of quantum fields. This is what is done in quantum field theory. So I'm getting a message here that my sound is not coming through so great. Let me just pause for a moment to make sure that
it's on, just not as loud. I just put my earphones on. So I could hear you a little better. But yeah, it's there, but not super.
Okay. I've got the right microphone on my settings, so maybe if I turn the volume up, I don't know if you'll have to let me know if you can hear me any better. Okay. Well, I'm seeing some messages that it's okay. So all right. I just want to make sure that you can hear
You're
me.
good, William. Just keep going.
Okay. All right. Okay. We'll get back to it then. All right. So we were looking at the idea that we shouldn't be looking at quanta as particles or as wave particle-like little objects, but instead as excitations of a field, often called a quantum field, because these are quantized harmonic oscillations of these fields. When you that's a more precise and accurate way to view what we call matter, substance. It's an excitation of a field. We could actually even get more precise than that it's a vortex dynamic in a super liquid medium. So the idea now is that a fundamental outcome of quantum field theory is that these quantum fields are never truly quiescent. There are always constitutive energetic fluctuations occurring in these ubiquitous fields, and hence there's the prediction of an ever-present non-zero energy in the vacuum state. In classical physics, a vacuum is totally devoid of energy or substance. In modern physics, however, all forces and associated particles are field-like, and their manifestation is a result of excitations of the respective quantum field. As such, according to quantum field theory, even in a vacuum, there are quantum fields. And importantly, these fields are always undergoing oscillatory excitations, even at the point where there should be zero energy. That is to say, there are constitutive zero-point energy fluctuations. These quantum vacuum energy fluctuations are not trivial. They're non-trivial. For example, as we are seeing in this simulation, in the theory of quantum chromodynamics, vacuum fluctuations are what gives hadrons, like the proton, their mass. So this is a visualization of a quantum field theory calculation showing virtual particles in the quantum vacuum, and specifically for the strong interaction. Even in supposed empty space, this vacuum energy is non-zero. What appears to be the ground state in one region of Kerr space will look different from the perspective of an observer where the spatial curvature differs. This is depicting calculations of the energy fluctuations of the QCD vacuum generating a quark-antiquark gluon condensate. And this is the energy that produces the strong interaction. and hence the nuclear confinement force. So immediately, our quantum vacuum fluctuations are, in conventional modern theory, are what give particles their mass. The so-called Higgs mechanism accounts for less than like 1% of the mass contribution of the hadron. I think I see a question. Ken, did you have a question?
Yeah, I was just curious. The simulation that we're looking at here seems to be relatively random in the way that this quantum foam is kind of coming up. Would you say that according to the models that you and the sim are working with, that this dynamic would be accurate, or would your model have a little bit more of a consistent vorticular flow?
That's a really good point you make, a really good observation. Yeah, because I think that even with this particular simulation, it's more of a example that's being given, because even within the more conventional theory approach within QCD, the fluctuations are much more organized within the proton itself. And certainly within the work that we've done with Nassim Haramein, the fluctuations are highly coherent. In fact, and that coherence would be observable if we had a more precise or accurate depiction being shown here. It would be a vortex. It wouldn't be these random fluctuations. You would be seeing a literal tornado or hurricane looking vortex structure. And actually, so that's the same calculations that we have are a highly coherent state of those energetic oscillators. And it actually also in QCD, it is seen as a sustained spatiotemporal pattern of the fluctuations in a vortex-like structure. And so what really distinguishes free space, empty space, from a particle where it looks like something's there, you've got the same energy density, the same amount of vacuum fluctuations, roughly, more or less. But the difference is that when those are highly coherent and in a sustained spatiotemporal pattern, like a vortex, particular motion, then it looks like there's something there. It looks like there's a particle there. And that's what distinguishes it from the more random fluctuations of free space, which would look more like this.
It seems like going into this topic would be a whole lecture unto itself, so I don't want to take away from what you're talking about, but I think it's a fascinating area.
Yeah, and it's a really salient point though to bring up. So yeah, but definitely that could be another lecture, another discussion.
Exactly.
Itself. Yeah.
Thank you, William.
Yeah. Thank you for the observation. So we have the theoretical basis for why we would expect there to be a non-zero energy value to even what is considered empty space. So we're beginning to understand that there really is no such thing as empty space. Empty space has a intrinsic non-zero energy, the 0-point energy density. Now, we know that this is the case. The substantive and energetic nature of the quantum vacuum is real. And these are a few examples of how we know that these energetic fluctuations of space are not figments of our imagination or artifacts of calculations in quantum field theory and renormalization and all of this. The first and foremost probably is the lamp shift, an observed shift in electron orbital energy level from predicted value. It's observed as a shift of atomic spectra and the magnetic moment of the electron. Now, this was the harbinger of modern quantum electrodynamics developed by Julian Schwinger, Richard Feynman, and Freeman Dyson. Julian Schwinger is, we're going to be looking at an experiment that has recently validated one of his predictions from his development of quantum electrodynamics and quantum field theory. The Schwinger effect. It comes from Julian Schwinger. Spontaneous emission. This goes back to Einstein and the photoelectric effect. This is how we make lasers. And quite literally, photons are being generated from the vacuum in a very coherent manner via excitation, quantized excitation of atoms. Zitterbewegung. That's a German term, German word for like a jittering motion. Trembling, I think, is its most closest translation. But from the Dirac equation for relativistic electrons in free space, it was predicted that there's an interference between positive and negative energy states that produces what appears to be a fluctuation up to the speed of light of the position of an electron. So this was predicted by Dirac. Dirac also predicted things like the positron. And he did that by positing that there's no such thing as empty space. That space is, in his case, what he was describing was space is full of negative energy electrons, the Dirac sea. And that's why electrons don't spontaneously drop to negative energy levels. There's nothing that says they shouldn't do that. They can't do that. In fact, they're supposed to go to the lowest energy level obtainable. So why aren't all electrons dropping to negative energy levels? It's because there's a infinite sea of negative energy electrons already occupying those levels. And so from the Pauli exclusion principle, other electrons are forced into positive energy values or higher, high energy values. But because of the constitutive interaction of electrons with this sea of virtual electron-positron pairs, now virtual only in the sense that we don't directly observe them, that they're not directly apparent to us. But because of the constitutive interaction, you have a jittering motion, and this has been observed with the electron. And then vacuum polarization. So around massively large compact objects like neutron stars and black holes, the quantum vacuum becomes polarized. This results in the Unruh-Hawking radiation. Now, Unruh-Hawking radiation has only been observed in analog systems, but this vacuum polarization has been directly observed in birefringence of light around neutron stars. And we'll take a closer look at that. But now it's been directly observed as well with the Schwinger effect. Now, regarding vacuum polarization, it was thought that the conditions necessary to create a polarization of the vacuum energy structure would require extreme conditions like the extremely large gravitational, magnetic, and electric fields around massively compact objects, i.e. Neutron stars and black holes. So this Schwinger effect, vacuum polarization, was thought we're only going to observe this around neutron stars and black holes. You know, there's this kind of black hole physics in that sense, and it's one of the ways that black holes create particles out of the vacuum. However, as we will see here, these astrophysical conditions have been replicated in the analog system and brought into the lab with clever utilization of graphene superlattices, in essence, enabling black hole conditions to be tested in the lab. Now, the most important example of the real substantive nature of space and the energetic energy flux of space is the Casimir effect. And this is another one that I think is by now really well known, but always important to point out, because if you don't know about it, you should know about it, especially when we're talking about the quantum vacuum fluctuations and their very real effects and manifestations. So the constitutive fluctuation of energy density of space on very short distances and timescales is not just theoretical. Its effects have been empirically observed and characterized, the most well-known effect of which is the Casimir force, which in its simplest form produces an attraction between uncharged objects that are at sub-micron distances, resulting in what is almost like a pressure differential, where the greater number of vacuum fluctuations outside the intervening space pushes the objects together. This effect generates a negative energy density, which is a demonstrable violation of the weak energy condition, a kind of law of physics that says negative energy density should not occur. And it generates an emergent attractive force. However, this effect has also been utilized to generate repulsive forces, generating veritable levitation. If you have like an asymmetric condition where one of these is a sphere, you can actually generate a repulsive force between them. And this is a potential means of generating levitation, because just by interaction with the quantum vacuum fluctuations, you could have an object levitate potentially. It has also been utilized to further demonstrate the substantive nature of the quantum vacuum via the dynamical Casimir effect, in which rapidly oscillating mirrors are used to generate pairs of real photons from the vacuum. And we have articles available on the RSF describing that. And importantly, there's also the dynamical Casimir effect, where the Casimir effect has been engineered to produce functional Casimir devices. So there are many potential technological applications of the Casimir effect, not least of which is an anti-gravitational force, if the effect could be sufficiently amplified and controlled. But here, a research team not too long ago reported on a non-reciprocal device based on quantum vacuum fluctuations that can affect unidirectional transfer of energy, like a diode. In a publication, this was published in the journal Nature Nanotechnology, and the research team reported a quantum vacuum mediated non-reciprocal transfer of energy between two micromechanical oscillators. It's one of the first times that demonstrated that this has been demonstrated. It's a breakthrough in utilizing quantum vacuum fluctuations to regulate energy transfer at the nanoscale and build functional Casimir devices. So similar to the control of electrical currents with diodes, the research team purports to have developed an efficient Casimir diode that can rectify energy transferred coupled by the Casimir interaction. So the non-reciprocity, that is the unidirectional energy transfer, is realized by dynamic modulation of the nonlinear Casimir interaction in a specially constructed optical cavity, in which frequency modes of membranes of two micromechanical oscillators are coupled using light and dynamically modulated to a special state of the frequency modulation called the exceptional point. That's what's demonstrated in these graphs of modulation frequency of these micromechanical oscillators. By utilizing the strong nonlinearity of the Casimir interaction and asymmetric structure near the exceptional point, it's possible to break the time reversal symmetry by modulating the separation between dual cantilevers, the micromechanical resonators, at the desired frequency and amplitude. So using this technique, researchers realized non-reciprocal energy transfer with the Casimir interaction. So this is one of those examples of, moving past is the idea of the quantum vacuum energy theoretical, or should we think of this as real or not? This is an example of understanding that it's very real, very substantive, and engineering devices based on that energy, that 0-point energy density of the vacuum. So we see this ubiquitous 0-point energy is not theoretical, but is observed in many natural systems, experiments, and even directly for technological application. And we are talking about a lot of potential energy. One reason why our research efforts here at the Resonance Science Foundation and with Nassim are focused on engineering methods that can harness the energy of the quantum vacuum, because there's a lot of potential energy there. Before renormalization, the vacuum energy density is calculated to be infinite. After renormalization, where you introduce a cutoff value, usually the Planck length cutoff value, so you can only have energetic oscillations, little quantum harmonic oscillators that are of the Planck length, nothing smaller. That's your cutoff value. When you do that renormalization process, then you get a finite number, and it's generally calculated to be about 10 to the 113 joules per meter cube. In a cubic meter, 10 to the 113 joules of energy. Now, I would be remiss if I didn't point out that that renormalization procedure is very arbitrary. I mean, there is some logic behind using the Planck length as a cutoff value for the size of your oscillatory modes of the vacuum energetic vacuum oscillations. But in the work we're doing, in the work Nassim has done, he's shown that undoubtedly there are sub-Planckian oscillators, sub-Planckian energy values. So really, the vacuum energy density probably is infinite. But we can take this number here. And so compared to the annual global energy consumption, I think one of the most recent values was estimated to be about 10 to the 20th joules for all of human civilization. So the amount of energy in a cubic meter of space could very easily satisfy the entire annual global energy requirement for human civilization. So just tapping that, a fraction of the potential energy there could satisfy our energy requirements nearly indefinitely. And probably if we were to realize that kind of technological capability to harness the quantum vacuum energy, the ultimate source of energy, that would almost immediately elevate us to a type 1 or 2 civilization on the Kardashev scale. Right now, we're a type 0 civilization. So this will be one of the most significant and momentous discoveries and technological applications of human civilization. And I mean, it will totally change the course of human civilization, because we will have a limitless clean source of energy. And we won't need hydrocarbon fuel sources. We won't even need solar energy sources, wind energy sources. If you can tap it directly from the quantum vacuum, that changes everything. And so it's actually something that is desperately needed and quickly. So this is very non-trivial considerations, non-trivial research. Now, as we were discussing a little bit, this QCD simulation is showing fluctuating gluons and quark gluon plasma. And this is how hadrons get 98 and actually, I think 99% of the mass. It's not attributed to the so-called Higgs mechanism. Now, what this means is that the strong force is the vacuum energy density. This is the same thing that Nassim points out in his paper, Quantum Gravity and the Holographic Mass. That the strong force, the nuclear confinement force, is the vacuum energy density. This is also what QCD is saying, except they have a little bit more how should I put this nicely, goofiness to it with the quark gluon plasma. Now, so your Planck density, so that's the 0-point energy density, the vacuum density, is what's producing the energy of the strong interaction. Now, in Nassim's work in quantum gravity and holographic mass, you get the exact value for the coupling constant between gravitation and confinement at the proton scale. That is the strong interaction but it's described in terms of a gravitational force, a strong gravity. So you've got your volume entropy R. That's your Planck density. That's the 0-point energy density of the vacuum. And it's calculated in terms of the quantum harmonic oscillators of the quantum vacuum. In this case, we're conceptualizing them as Planck spherical units. So little spherical oscillators, or you can even think of them as spherical vortexes. And this goes back to the insight that Ken pointed out, shared that there's a very definite structure here because these are overlapping, these little spherical oscillators of vortices are overlapping, so you get optimal packing in the volume of R here. Now, the holographic ratio between the surface entropy, the value of those Planck spherical units packed along the surface, overlapping along the surface. And so the holographic ratio between that and the volume entropy, and entropy in this case also means like information, like a Shannon entropy, that gives you this holographic ratio. This is a universal constant, phi here. With eta over R, you'll get the mass of any black hole. The reciprocal, R over eta, you'll get the mass of, at the hadron scale, the mass of a proton. And so we can see 2 phi times the Planck mass. So that's the Planck energy density here with this factor of 2, which shows up quite often in physics. We can take that and when we square these terms, we get 4 pi squared h bar times the speed of light over g, the gravitational constant. And when you calculate this, it's at 5.89 times 10 to the negative 39. That's the exact value for the coupling constant between gravitation and confinement at the proton scale, or the strong interaction, the holographic mass ratio. So phi demonstrates the quantum gravity confinement from the vacuum energy density. So, again, the quantum vacuum energy density here is what is producing, when it's in this highly ordered coherent state, is what is producing what we call particles, mass energy. Now, here we're showing in a way that is fully compatible with general relativity, how that strong interaction, the nuclear confinement force, is a quantum gravitational force. And that's one of the primary differences between how we're taking that vacuum energy density and how it's being utilized in that QCD simulation, in QCD calculations. So hence the gravitational force coupling constant is computed directly from the geometric relationship of the Planck oscillator surface tiling to the interior vacuum oscillations of the proton. Consequently, the unifying energy required for confinement is generated by holographic derivations directly from first principles, or simple geometric Planck vacuum fluctuation relationships. And so this is one of the reasons why having a good understanding of the nature of the quantum vacuum, why it's substantive, and why it has very real effects, is critical. It's very significant to understanding unified physics and quantum gravity. Furthermore, the rest mass of the proton is computed without requiring the complexities introduced by a Higgs mechanism, which also utilizes a non-zero vacuum expectation value. As well, we can take the same generalized holographic approach and solve one of the largest problems and one of the greatest problems in predictions from the standard model, the vacuum catastrophe. So we saw that vacuum energy expectation value of 10 to the 113 joules per meter cubed. However, so that's coming from quantum field theory, from quantum mechanics. That's the vacuum energy expectation value, VEV. However, from cosmology, the observations and calculations from cosmology calculate the VEV as estimated around 10 to the negative 9 joules per meter cubed. And one of the reasons for this is that if space had this energy density everywhere, 10 to the 113 joules per meter cubed, it would be highly curved. Space would be highly curved, almost infinitely curved. But cosmologists say, no, space is almost flat. It's not curved at all, empty space, free space. So they say, it's 10 to the negative 9 joules per meter cubed. But if you go back to quantum field theory, to quantum mechanics, it says that space is nearly infinitely curved. And in fact, that's called the quantum foam, quantum vacuum foam, because there's so much energy in those vacuum oscillations that it's generating a multiply connected space-time geometry, a micro wormhole network at the Planck scale. So quantum field theory, quantum mechanics says that space is nearly infinitely curved and multiply connected. But cosmology wants to say, no, the universe is flat. Now, it's actually, I believe quantum field theory has it right, that space is nearly infinitely curved. even in what we think of as empty space and free space. And that has a lot to do with the experiment that we're going to be looking at, the vacuum energy teleportation protocol. But nevertheless, this is a 10 to the 122 order discrepancy between these predicted values. Now, Nassim resolves this discrepancy by showing that, one, we are in the interior of a black hole. So this is like the critical mass of the universe. We're inserting the generalized holographic ratio phi, the Planck mass, Planck vacuum energy density. We're calculating that out, and that is equivalent to the Schwarzschild solution to Einstein's field equations. So we're inside a black hole. So that's one of the reasons why space is actually infinitely curved. If you're in the inside of a black hole, you'd expect space to be very curved. Now, the generalized holographic model describes how any spherical body can be considered in terms of its PSU packing or volume entropy. And that's, again, harkening back to the fact that those quantum harmonic oscillators, the Planck spherical units, are highly ordered. It's not random fluctuations when you're talking about like the proton or organized matter. But the generalized holographic model describes how any spherical body can be considered in terms of its PSU packing or volume entropy, which we saw as the term R. As the radius of the universe expands from the Planck scale to the cosmological scale, the resulting change in density from the vacuum density at the Planck scale to that at the cosmological scale yields an exact equivalent to the currently observed critical density of the universe. Therefore, from the generalized holographic approach, which describes how any spherical body can be considered in terms of its PSU packing, it's shown that the scale relationship between the PSUs and a spherical shell universe resolves the 122 orders of magnitude discrepancy between the vacuum energy density at the Planck scale and the vacuum energy density at the cosmological scale. The results described in this paper show how, as the density changes with radius, we have a scalar field that is coupled to gravity and thus rolls down a potential governed by a generalized holographic quantized solution to gravity. From quantum field theory, we know that continual and constitutive energetic fluctuations are expected. And all of space is filled with quantum harmonic oscillators. Here we see a depiction of these energetic fluctuations. In this case, depicting the creation-annihilation cycle of a particle pair in the quantum vacuum, like a positron-electron pair. This is another way in which the quantum vacuum oscillations are often described as this continuous cycle of particle pair creation and annihilation, basically going from mass to energy to mass, and a continuous cycle. If these mass energy fluctuations are occurring all the time and are of significantly high energy, why is it then that we are not more aware of this infinite sea of energy and the substantive nature of space? One reason is that the quantum vacuum in free space is in a state of equilibrium. If you think about this in terms of matter, it has an infinite number of particles and their antiparticles, so that at a macroscopic scale that we're observing it from, they completely cancel out. So in little and small regions on short time scales and in small regions, you can have very large energy that would be observable. But that's very small scale. So when you go out to a macroscopic scale that we're experiencing the vacuum energy density at, it all kinds of averages out. It's like net zero. Is for every particle, there's an antiparticle. For every positive charge, there's a negative charge. And so to us, it looks like nothing's there. There's nothing to interact with. Similarly, for other fields and forces, space is infinitely positively curved and infinitely negatively curved. So that at a macroscopic scale, it appears flat. That's where we get the erroneous value for the cosmological constant. So the cosmology is saying that vacuum energy density is 10 to the negative 9 joules per meter cubed, because at that large of a scale, the infinite positive curvature and infinite negative curvature cancels out, and that's roughly flat, roughly even. So it's only in conditions where there is a gradient in the structure of the vacuum that particles, energy, or forces are observed. This is going to be a key insight for us on a technological development application of harnessing the quantum vacuum energy. You need a gradient, polarization in the field, so that averaging out isn't a net zero energy. You need a gradient so that it can be harnessed. So for instance, spin induces a gradient in the structure of space. That's one of the reasons why it's expected that the vacuum fluctuations in the hadron, in the proton, are a vortex. Why there's spin there? Because that induces a gradient in the structure of space. So if you picture space as comprised of infinite little polarizable units, then vortices in this quantum vacuum plasma will appear as substantive, having mass, charge, and binding forces like strong gravity and electromagnetism. Another way to describe the formation of a gradient in space is vacuum polarization. And indeed, it has long been predicted that with sufficient vacuum polarization, the particles that abound in the vacuum will be released, freed, emitted. This is the case with the Hawking-Unruh effect. In this case, it's strong gravitational curvature that's producing your gradient in the vacuum structure. And that's what enables the particles, the particle pairs, to dissociate. And in the focus of our discussion here, the Schwinger effect is another way to generate this vacuum polarization. And instead of an extremely strong gravitational field, you have an extremely strong electrical field that is causing your ability to separate those balancing yin-yang particle pairs. So if you get a strong enough electrical field, you can actually get those positron-electron pairs of the quantum vacuum oscillations to dissociate. In the quantum field extension of the idea of the Dirac sea, I remember I had mentioned that a little bit earlier, that Dirac explained the positive energy value of electrons by positing that there's an infinite sea of negative energy electrons, and as well holes in that, which are called positrons. This has since been extended into the idea of a quantum field for leptons, but one of the energetic modes of the quantum vacuum are these electron-positron pairs. Now, no electrostatic field is measured at a macroscopic scale of the vacuum in free space because the negative charge of the electron is balanced by the positive charge of the positron. as are their mass, spin, momentum, and other properties. However, if we were to generate an extremely strong electrical field, then instead of continuously cycling between creation and annihilation, the different charges would cause the particle pairs to accelerate in different directions in the electric field. The electric field is increasing. Under such a condition, the particles would appear to emerge from the quantum vacuum, and you would have observable electrons and positrons generated in the extremely strong electrical field. And this is the Schwinger effect, first hypothesized by Julian Schwinger over 70 years ago. In the Schwinger effect, matter is created from a strong electric field. Vacuum polarization causes emission of those electron-positron particle pairs. And this, in a sense, is a decay of the electron field. Essentially, the electric field can only become so strong before all that energy in the field just starts going to generating electrons and positrons from the quantum vacuum. That's another way to kind of look at it. Now, the Schwinger limit, the field strength, the electrical field strength needed for this vacuum polarization, as predicted by Julian Schwinger, is actually very large. 10 to the 18 volts per meter, or 10 to the 9 Tesla. That's the magnetic field strength needed. Now again, this is thought to only be found, these kind of field strengths, a billion Tesla and 10 to 11, a billion to a trillion Tesla, or 10 to the 18 for your electric field strength. This is thought to only occur around objects like neutron stars and black holes, massively compact astronomical objects. And in fact, the Schwinger effect is analogous to Unruh-Hawking radiation, where instead of an electrical field, it's the extremely strong gravitational field of a black hole that causes separation of the vacuum particle pairs. In both instances, a gradient is being generated in the vacuum energy density that causes mass energy to be extracted from the vacuum. And this is a key consideration in developing technologies that can tap the quantum vacuum energy. The key is to generate that gradient in the vacuum structure. And indeed, the field strength involved for both effects are so strong that it's thought to only occur around neutron stars and black holes, high energy astronomical objects. These are often also called magnetars when they have those extremely high magnetic field strengths of a billion or more Tesla. This property of black holes to generate particles and energy from the quantum vacuum is one reason why researchers at the Resonance Science Foundation consider black holes as engines of mass energy creation. In fact, such astronomical objects are the natural laboratories for testing these theories of matter creation in quantum field theory, and for testing the substantive nature of the vacuum. However, for things like vacuum polarization, we need an analog system, a more clever mechanism for testing these extremely large field strengths producing vacuum polarization, because right now it's not entirely feasible to create a little neutron star or black hole in the lab. But there are other ways of simulating those kind of conditions. And that's what we're going to review here, the experiment that did just that. Now here, this is from a report showing birefringence of light from a neutron star as it passes through the polarized vacuum structure. So the magnetic field of the magneton is so strong that it's ordering the vacuum into like a crystalline phase. That's like spatial symmetry breaking. vacuum polarization. And the light passing through it undergoes birefringence, like it was passing through a crystal. Crystals oftentimes cause birefringence of light. And this was observed, this birefringence of light from a magnetar as it passed through the vacuum space due to the ordering dynamic that the strong magnetic field of the neutron star had on the vacuum structure. So this is another example of where the substantive nature of the vacuum has been directly observed. And an important thing to note is that particles that are produced in this way, like a particle-antiparticle electron-positron pair, are necessarily quantum entangled with each other. And so this is going to be important when we look at the intrinsic entanglement of the quantum vacuum and how that was leveraged for quantum energy teleportation. And when we consider the ER equals EPR holographic correspondence conjecture, that is Einstein-Rosen bridges Einstein-Podolsky-Rosen correlations, wormholes equal entanglement, we're also talking about micro wormholes and quantum entanglement. And we're talking about these particles being generated from the vacuum structure. And there was a report on the holographic Schwinger effect and the geometry of entanglement, where they were showing how this mechanism of the Schwinger effect is a way to realize what's called the Wheeler wormhole. John Archibald Wheeler in quantum geometrodynamics, a unified physics, a quantum gravitational approximation of unified physics, he described electrons and positrons as a wormhole, as a particle pair, with the positron and electron as mouths of a connected Einstein-Rosen bridge through space. And that idea has, in this study, has been validated. So in the experiment, it was thought that the field strength necessary to produce these vacuum polarization effects would only be able to occur around neutron stars and black holes. So that kind of makes any earthbound laboratory experimental test of predictions like the Schwinger effect seemingly impossible. However, in a recent experiment, this was reported in the journal Science, an international team of researchers utilized a phenomenal property of graphene to observe the Schwinger effect for the first time and validate the Schwinger effect. Now, graphene has become a focus of material scientist research as it has remarkable structural and electronic properties. For example, it can carry huge current densities, about 10 to the 8 amps per square centimeter, roughly 2 orders of magnitude greater than copper. And even though it occurs in these single planar honeycomb configurations or sheets, it's remarkably strong. If rolled into a carbon nanotube, it's stronger than steel. Researchers have purported to observe superconducting properties in graphene, something that is usually only observed in supercooled metals or metal alloys. And this is opening the potential for room temperature superconductors. Another technological application that will have significant benefits for human civilization, room temperature superconductor. So in the experiment, these researchers constructed what are called graphene superlattices. Now in graphene, a vacuum exists at the point where the material's conduction and valence electron bands meet, and no intrinsic charge carriers are present. So you have a kind of artificial vacuum set up. And in recent experimentation, this research team identified a signature of the Schwinger effect at this so-called direct point, observing pairs of electrons and holes, the solid-state equivalent of positrons, created out of that vacuum space in the graphene superlattices. The team achieved this by constructing devices that are referred to as graphene superlattices, where essentially each planar crystalline lattice of carbon atoms are stacked but slightly misaligned, enabling nonlinear electronic interactions between atoms in the lattice. In these graphene superlattices, graphene's unit cell, the simplest repetition of carbon atoms in its crystal structure, significantly expands such that the crystal is stretched by a factor of up to 100 in all directions. This stretching dramatically changes the material's properties, enabling the researchers to produce electric field strengths of a quintillion volts per cubic meter or square meter. The team achieved this by constructing devices from what are known as the graphene superlattices and leveraging that kind of nonlinear interaction at that direct point. So via this kind of construction, they were able to directly observe the production of an electron-positron plasma and key signatures that demonstrated the realization of the Schwinger effect. Current voltage characteristics that resemble those of superconductors, sharp peaks in differential resistance, sign reversal of the Hall effect, and a marked anomaly caused by the Schwinger-like production of a hot electron hole or electron-positron plasma. So by applying strong electrical currents to the graphene superlattice-based devices with current densities up to 0.1 microampere per millimeter, the team was able to identify current voltage characteristics that only occur with the production of electrons and positrons. But one of the significant things of this experiment is that they didn't have to produce electric field strengths of 10 to the 18 volts per square meter. They were able to work with much more achievable current densities and leverage that kind of nonlinear behavior of these graphene superlattices, the conduction within these graphene superlattices, to generate a strong enough effect for vacuum polarization that a electron-positron plasma was generated from empty space, from the quantum vacuum. So where before there was just a vacuum in between the graphene superlattices, they generated an electron-positron plasma, a particle flux. Surprisingly, the team observed another unusual high-energy process that has, as yet, no analog in particle physics or astrophysics. When the researchers filled the vacuum in graphene with electrons and accelerated them to the maximum possible velocity allowed in the material, which is actually around 1/300th the speed of light, So it's not the speed of light in a pure vacuum. The electrons appear to become superluminous. So they exceeded that theoretical bound. So 1/300th the speed of light is the maximum speed of light in this substance. They exceeded that speed limit. Under such a condition, the electrons provided an electrical current much greater than that allowed by theory, which the researchers further attributed to the spontaneous generation of additional production of electron-positron plasma out of the vacuum in the graphene superlattices. With the one of the effects of these particles being released from the quantum vacuum was that other electrons in the conduction bands were being accelerated faster than the speed of light that was thought to be possible in that medium. The increased conduction resembles that of superconductivity to such a high degree that the researchers actually suggested that some previous reports of superconductivity in special configurations of graphene could have been observations of Schwinger-like production of electron-hole plasma rather than evidence of superconductivity. They actually suggested that previous reports of superconductivity in certain special configurations of graphene were in fact vacuum polarization and Schwinger-like production of electron-positron plasma. So this is a very interesting outcome that not only can we leverage the special properties of these graphene superlattices to produce particles out of the vacuum, get a particle flux from the quantum vacuum, but that process may also be instrumental in achieving room temperature superconductivity. So a kind of concluding thought from this, we've reviewed the nature, the theoretical development of the quantum vacuum, experiments and observations that have directly observed and verified this substantive and very real nature of the quantum vacuum. And probably a single kind of concluding substance is that nothing does not exist. The idea of empty space of a true vacuum is purely theoretical. It's not something that really actually exists. We are in a sea of energy. One of the central aspects of the unified physics of Nassim Haramein and the Resonance Science Foundation is that space is not empty. It is substantive and absolutely saturated with mass energy, just as quantum field theory says it should be. Interestingly, although this is a central aspect of physics and quantum theory, many scientists still seem to consider space as empty. And in many reports about that experiment that we just reviewed, it was in many popular articles and many commentators, almost all of them described it as scientists created something from nothing. But we know better. Nothing does not exist. Those particles were always there. They just found a way to generate a gradient in the structure so that they would be liberated in a sense. And then you could see what was always there in actuality. So that's the intrinsic energetic nature of space, but an equally important aspect of that energy is that it is intrinsically quantum entangled. The vacuum state is an infinite source of quantum entanglement. And this is a concept that I explore in one of my publications, Unified Physics and the Entanglement Nexus of Awareness. So that entanglement nexus is referring to the fact that you've got this vacuum energy density ubiquitous vacuum energy density, connecting all things, and it's strongly spatially correlated, i.e. quantum entangled. And this again goes to the idea of the Wheeler wormhole particle pair, or the ER equals EPR holographic correspondence conjecture. The idea that not only do you have this continual particle-antiparticle pair creation and these quantum harmonic oscillations of quantum fields, but also space, the gravitational metric, is infinitely positively curved and infinitely negatively curved. So all of those oscillations, those little vortices in the superfluid medium, are connected via wormholes, i.e. quantum entangled. So somewhat briefly, we'll look at a experiment. Actually, there was 2 experiments back to back by independent groups that demonstrated this intrinsic quantum entanglement of the vacuum in what's called the quantum energy teleportation protocol. In addition to being a direct demonstration of the ability to leverage the intrinsic entanglement state of the quantum vacuum to teleport energy, the protocols have potential applications in a wide variety of quantum devices and quantum information technologies like entanglement harvesting, considerations of the parallel of quantum energy teleportation with wormhole qubit teleportation, ER equals EPR, understanding quantum thermodynamics with applications in maintaining robust qubit entanglement, for instance, in quantum computers, and many body quantum systems, and even greater understanding and insights into things like black hole entropy, thermodynamics, and information. So we reviewed the substantive and energetic nature of space, in which there are constitutive energetic fluctuations, even in a complete vacuum, what is called zero-point energy or quantum vacuum fluctuations. The real and substantive nature of quantum vacuum fluctuations exhibited in the Casimir effect, the dynamical Casimir effect, Casimir torque, repulsive Casimir force, the Schwinger effect. Of high salience to the study discussed here, the Casimir effect has been leveraged to engineer functional Casimir devices like Casimir diodes, such that the quantum vacuum energy can be utilized for the non-reciprocal or unidirectional transfer of energy between 2 systems. We also reviewed the experiment that directly demonstrated the ability to draw energy and even matter from the quantum vacuum fluctuations with the graphene superlattices. Now, an additional important consideration is that intrinsic spatial entanglement of zero-point or quantum vacuum fluctuations. The importance of this non-local entanglement network has been discussed in detail in our publication, The Entanglement Nexus of Awareness and the Unified Space Memory Network. And it's being actively utilized in quantum experiments where entanglement is literally being harvested or farmed from the quantum vacuum to strongly correlate systems without them ever having to come into direct interaction. 2 quantum systems can be entangled just by bringing them to the ground state, the vacuum state. Once they interact with that entanglement nexus, they don't even have to have any kind of physical exchange, any kind of exchange of photons or any kind of interaction. They can become quantum entangled spatially and temporally just by harvesting the intrinsic entanglement of the quantum vacuum. Considering the spatial entanglement of quantum vacuum fluctuations, it should be possible for an observer who accesses information about the zero-point fluctuations in their local vicinity to simultaneously gain information about local fluctuations around a distant observer via the non-trivial correlation between the two observers induced by the vacuum state entanglement. For reasons that we will explore, such an instantaneous accession of information between non-local systems or observers requires a classical communication channel between the observers as well as local operations to access the vacuum state correlations in their local regions. So it's not quite our quantum communication in full yet, a nearly instantaneous communication, since it still requires a classical channel. Now, a version of this is already used to teleport information between two systems, and we've reviewed this in our last session, the quantum teleportation methodology. And we reviewed this in the traversable wormhole teleportation protocol experiment. And the recording for that is available in the Members Hub on the Resonance Science Foundation website. However, there are other potential quantum teleportation case scenarios. This was just information, teleporting a quantum state of a system of qubits from one quantum system to a secondary quantum system. But it should, in principle, be possible to teleport other physical quantities, especially by utilizing the universal entanglement of the field, such as teleportation of energy between two systems or observers via the vacuum state entanglement of their local regions. And that is what is called quantum energy teleportation. So consider, for example, two observers who, Alice and Bob, who want to teleport a quantity of energy between themselves using the entanglement nexus of quantum vacuum fluctuations. As we have discussed, the field possesses 0-point fluctuations, but as well, there's non-trivial correlations of the field induced by vacuum state entanglement. So if Alice obtains information about a local fluctuation around her through a measurement, she simultaneously obtains some information about a local fluctuation around Bob via the correlation. Although the average value of the vacuum energy density in Bob's region remains 0 after Alice's measurement, Bob's local field in the post-measurement state can carry a negative energy density depending on Alice's measurement result. When the result indicates the positive energy case, Alice sends Bob's a message via classical communication channel. So this is one reason why this isn't going to be instantaneous, because it's still obeying the structure of causality and the relativity of simultaneity, because she has to send this no faster than the speed of light, a classical communication channel. But she takes a measurement, in doing so, injects energy into the system. Now, her local vacuum oscillations now have a positive energy density. She relays that state via message to Bob. Now, Bob, timing it just right, can access via a local operation the vacuum fluctuations in his local vicinity and extract energy from the field. And in a sense, in a way, this would be akin to Alice having teleported the energy to Bob, because she doesn't send the energy via any kind of classical channel. She injects the energy into the vacuum energy fluctuations around her, tells Bob about it. Bob times it so that he can retrieve energy from his local vacuum fluctuations because they are quantum entangled. I see a question come up. Carrie, would you like to unmute yourself? Good.
Yeah, thank you so much. forgive me, this seems a bit tangential, but I'm very curious if this can speak to interspecies communication and telepathic communication, where there really isn't a classical means of communication. It really is all moving consciousness through the field. This is the direction my work points in, and this is just super exciting. So could you speak to that a little bit, what you guys are aware of?
Yeah, well, actually, in my mind, that's not tangential at all, because and actually, this is a concept that I explore in that paper I mentioned, the entanglement nexus of awareness.
Yes.
In that I believe that primarily, fundamentally, communication occurs in a manner very similar to this here.
Yes.
That we're interacting with the field. You could think of that as our thoughts or feelings having an energetic exchange with the field, because those have those physiological correlates of our thoughts have a spatiotemporal electromagnetic pattern, or heart rate, the electrical impulses of our heart. Those are all very energetic actions that physiologically correlate with our thoughts and emotions and these kind of things. That's energy affecting the fluctuations of the vacuum energy density in our local region. And because those are correlated spatially or quantum entangled with the vacuum energy density fluctuations around another being or person, whether animal, they can access that information and what would probably be called telepathically. So via the intrinsic entanglement between all systems, you can have non-local exchange of information.
Yeah, thank you. It's just so wonderful, the work you're doing to put more language to what is for some of us intuitively and inherently clear and obvious, but we haven't had a multidisciplinary way to speak to it. And more people are asking for different ways.
So great questions there. Now, just to finish up the thought on this, the background for the experimental setup here, it has very much to do with the timing of these operations, the classical communication, where Alice communicates her measurement that injected energy into the local quantum vacuum fluctuations of her vicinity. She obtains a positive energy density. She communicates that to Bob in such a way that, and it's timed in such a way that Bob can perform a local operation, kind of like another measurement, in which he can extract energy from the quantum vacuum in his local vicinity. So some key considerations in this is that this isn't exactly harnessing quantum vacuum energy in the fullest capacity, in the truest sense, because there's a balanced conservation of energy in this sense. Bob is only extracting an amount of energy that is commensurate with what Alice injected into the vacuum energy density. And he's able to do so because of the spatial correlation, the quantum entanglement between the two regions. It's necessarily occurring at or below the speed of light. So this isn't a instantaneous signaling or teleportation scheme yet. And there's these first initial most experiments that have successfully demonstrated this proposal. The proposal comes from Masahiro Ota, and he's just done a lot of phenomenal work with better understanding the nature of the quantum vacuum and how to harness potentially energy from the quantum vacuum. So it's more than 15 years ago that Masahiro Hota developed and proposed the protocol for teleporting energy via that scheme that we just looked at. And he has many ideas that I would love to quote, but one that I definitely need to share from one of his publications, one of his papers, quantum fields and vacuum states carry an infinite amount of quantum entanglement. And so this goes back to the idea of entanglement harvesting, entanglement farming, or even how two systems, maybe even two people, two organisms separated in space can have in a connection, in exchange, without the kind of normal direct physical interactions via this infinite amount of quantum entanglement, the entanglement nexus of the quantum vacuum. So in the experiment, it was actually done using organic polymers, molecules. And one of the things that had to be overcome in order to do this quantum energy teleportation protocol was this restriction called strong local passivity, SLP. And basically what this restriction says is that if you have a system of connected particles, these are correlated to some degree, you know, whether it's a mixed state or a pure state, but there is correlation between these. And if they're in the ground state, they are fully quantum entangled. The ground state is another term for the vacuum state, because the vacuum has infinite quantum entanglement. Now, if you were to inject energy, so that's Alice's measurement, right? If you were to inject energy into the system, you wouldn't be able to tap it or access it from one of the subunits of that system, because the energy will be distributed via all of them nearly instantly and equally, because they're quantum entangled. So energy that goes to one of the subunits is going to be almost instantly distributed among all of them. And so you can't draw energy from one of the subunits. So if one of these was representing Alice and the other was representing Bob, you couldn't achieve that quantum energy teleportation because the energy that goes in with Alice's measurement, the energy that she would inject into her, the vacuum state around her, would be instantly distributed through the entire system. But the researchers came up with a mechanism for breaking this strong local passivity with what are called local operations and quantum classical communication. So timing this local measurement just right, communicating that outcome to one of the subunits, they can then perform a secondary measurement that draws energy from the vacuum state quantum entanglement. Yeah, so the main hurdle to overcome with actually being able to do this experimentally and demonstrate it is that any local action taken on a single subunit to extract energy will result in energy spreading through the entanglement network, merely raising the total energy of the system. However, there is a way to activate entangled ground states of a multi-part quantum system in such a way that energy injected into the system can be extracted from a single distal subsystem via the local vacuum energy density and the intrinsic entanglement of vacuum state. And that is something that was done by, led by Eduardo Martinez. And this is a researcher that has done, like Jota, some really phenomenal, remarkable work with, moving past the idea of are the quantum vacuum oscillations theoretical, or are they real or not? They've moved past that, and they're developing methodologies and technologies to actively harness the energy of the intrinsic energy of the vacuum and the intrinsic entanglement. So Eduardo Martinez has done a lot of work on developing protocols for entanglement harvesting. So he calls himself a space-time engineer, and I think that's an apt moniker. He's a space-time engineer. And his research team have presented the first experimental activation of strong local passive states and the first empirical demonstration of quantum energy teleportation as originally proposed by Jota. So their experiment confirms for the first time that establishment of entanglement in the ground state of a multi-partite quantum system and performing the local operation in classical communication protocol allows for the activation of localized zero-point energy density without energy transfer through the entire system, so obviating that SLP restriction. The energy can be accessed freely and instantaneously via the intrinsic entanglement of the field, essentially a teleportation of the physical quantity of energy of the quantum system. And here it is reported just last March. So the experiment performed by Eduardo Martinez and his fellow researchers used a nuclear magnetic resonance to induce quantum entanglement between carbon atoms and an organic polymer molecule. When the organic polymer molecule is specifically resonated with magnetic fields and radio pulses from the nuclear magnetic resonance device, the researchers were able to induce the ground state of the atoms in the molecule to become quantum entangled. This mimics the intrinsic state of spatial correlation in the entanglement nexus of the quantum vacuum. So if we recall that depiction of Alice and Bob, that was depicting very specifically them accessing in a very natural way the quantum vacuum energy density and its entanglement network. In this experiment, they're kind of artificially inducing replicating that quantum vacuum entanglement via the ground state, inducing the atoms, the carbon atoms in this molecule to go into the ground state. That's their vacuum state. A finely tuned series of radio pulses from the nuclear magnetic resonance device entangles the ground state of the carbon atoms. And we've got A for Alice and B for Bob. The intermediary carbon atom, AN, could then function kind of metaphorically as a messenger between A and B. So this is your classical communication channel by analogy. And transfer the entanglement state of A to AN via resonance transfer with a secondary radio pulse and a final pulse aimed at B and the intermediary atom AN simultaneously to transmit the information of the excited ground state of A to B, enabling B, our carbon atom C3 here, to access the excited ground state of A via the non-local entanglement network, breaking the SLP state, strong local passivity, and releasing energy from B. So the researchers, with these finely tuned radio pulses, the timing is pretty critical in this experiment, they induced the system into the vacuum state, the ground state of the polymer. Everything becomes quantum entangled at the vacuum state, the ground state. They have a second pulse that sends the information of the entanglement state of A to AN, and then a final pulse that transfers that from AN to B. B essentially accesses the information of the entanglement state of A, and that energy is released by B. The researchers recorded the release of that energy from B and demonstrated that the energy was quantum mechanically teleported between the two carbon atoms in the polymer. So, you know, it was like a simulation in a organic molecule, in a polymer, and you could extrapolate out where, okay, A and B aren't carbon atoms in a resonance chain of a molecule, but are two people like Alice and Bob. And instead of the ground state of the molecule, they could use the vacuum state of the quantum vacuum. So via this experiment, it's very possible that we could develop technologies that teleport energy quantum mechanically. And this has some very interesting applications and implications. But note that this is more like a simulation of vacuum entanglement, where the ground state of the carbon atoms is playing the role of the quantum vacuum that naturally contains spatial correlation for all systems. In this case, the entanglement is being induced, that is entanglement harvesting, by bringing the carbon atoms to the ground state. However, in future experiments, it should be possible to run the experiment in intrinsically quantum entangled systems, in which the entanglement does not have to be induced, but is present via the naturally occurring spatial correlation of the quantum vacuum energy density. And Masahiro Hota has said that that's what he would like to see next, the next step on that. This was only one of the experiments, but to me, it's one of the more exciting ones. There was a secondary experiment performed by a researcher, a physicist named Ikeda, who was actually a student of Hota's, and he was able to demonstrate the same kind of quantum energy teleportation using quantum computers, IBM, free use, publicly available quantum computers. And so the details of that are available in the article that this review is based on. But as can be seen here, after repeated measurements, the researchers reported an average decrease in the energy of carbon atom B. Goes down here. There's higher energy value, and then as the protocol is repeated, the energy value of B goes down as energy is being released. So that's like drawing energy from the system. You're accessing, harnessing that energy. This has important implications for multipartite quantum systems, like the qubit systems in the quantum computer, because this is a potential mechanism to draw energy from them to keep them super cooled. So cooling, keep them in a quantum entangled state using this protocol. So this could have direct applications in increasing the robustness and efficiency of quantum computers. Now, while it would normally take almost 700 milliseconds for the energy to travel via normal dispersion from A to B along this polymer molecule, the researchers showed that with the QET, quantum energy teleportation protocol, it took no longer than 37 milliseconds for the entire energy transfer process. So that's about 20 times faster than the classical case scenario of energy propagation along the molecule. It went from 700 milliseconds to 37 milliseconds. Again, thinking about technological applications for this, if we had a long distance quantum energy teleportation protocol, you could potentially send energy or signals 20 times faster than via classical channels. And actually, so that's one of the things that Hota describes is a long distance quantum energy teleportation using another special state of the quantum vacuum called a squeezed state. You know, we looked at vacuum polarization. Now, again, though, this isn't going to be instantaneous because with this protocol, it still requires this classical communication channel. So although it is potentially like 20 times faster in some case scenarios, like what was observed with the energy transfer along the organic polymer, this isn't going to be instantaneous yet. But there is actually a article I just published that describes a mechanism for real quasi-instantaneous teleportation. And actually that might be our next unified physics review. I was just clicking through to see if I had anything on that. Now, ideally, to truly realize Hota's original quantum energy teleportation protocol, zero-point energy would be harvested from systems whose ground states naturally features quantum entanglement in the same way the fundamental quantum fields that permeate the universe do. This would enable some exciting possibilities like long-range quantum energy teleportation, utilizing this squeezed state. From an informational viewpoint, the spatial correlations of the zero-point fluctuations, including quantum entanglement, decay as the distance becomes large. So that's one of the reasons why in the kind of communication we might call telepathic, it does have some variability in the strength depending on your proximity to the sender and receiver. But Hota has a mechanism for long distance quantum energy teleportation, and it has to do with inducing a squeezed vacuum state, which is a very interesting methodology that produces this abrupt expansion of the space where quantum fluctuations of the field become severely stretched. And in this way, he can kind of chain the quantum entanglement over much larger distances, the strength of the spatial correlation over much longer distances. So there's future experiments already being proposed and in the works that should be very exciting, and the technological applications of this are going to be huge, not least of which because this is really getting into space-time engineering. And it's via space-time engineering that we're going to get the kind of technological capability to harness quantum vacuum energy, to develop gravitational control technologies, and other very important applications of being able to directly harness the quantum entanglement, the intrinsic non-local connectivity network of the quantum vacuum, like instantaneous communication or signaling. Those things become possible when you begin engineering the space-time metric. So communication via like a wormhole, maybe even travel via a wormhole. So this gets into very interesting and exciting potential applications. But to this day, scientists and popular commentators alike are still inclined to refer to the vacuum as empty and nothing, despite the myriad theoretical and empirical demonstrations of the substantive nature of the quantum vacuum. We've actually just kind of looked at kind of briefly a few examples, but after going through that, it almost is incredulous that physicists will still, and maybe even non-technical people will still regard the quantum vacuum energy, and so that the energy of space that's all around us that makes us is somehow not real, somehow just imaginative. Hopefully after this review, we're all on the same page that there is no doubt about the very real and substantive nature of that energetic flux of space and quantum entanglement, connectivity, non-local connectivity of the unified field. So at this point, it's probably time to stop referring to space as empty and the vacuum as nothing. Even if it gives kind of an air of mystique to these experiments, saying like, physicists or scientists draw energy out of nothing, but it promulgates a common yet erroneous notion of the fundamental nature of our reality. And it's time to acknowledge the paramount logical conclusion: nothing does not exist. It's time for scientists and engineers to begin taking the quantum vacuum energy seriously and further exploring ways in which we can harness the nearly limitless energy potential of zero-point energy density for space-time engineering, quantum communications, including potential non-local communications, and of course, energy generation technologies. As an additional interesting consideration, we have the traversable wormhole teleportation protocol. So it's very interesting to consider the quantum energy teleportation protocol in terms of that ER equals EPR holographic correspondence conjecture. And that is explored a little bit further in an article that I just posted to the Resonance Science Foundation on counterfactual communication, quantum communication protocol, and having a very a full realization of teleportation and sending information and energy via wormholes. So thank you all for participating with me, and I hope that we all learned some things, gained some greater insights into unified physics, and the exciting developments that are almost accelerating every day. In just the last few months, there's been the traversable wormhole qubit teleportation protocol, the quantum energy teleportation protocol, producing particles from the quantum vacuum with the Schwinger effect. And so it's a very exciting time for the development of unified physics, as quantum gravity theories are going beyond just the theoretical purview, and they're being tested empirically in the lab. And of course, that's kind of the most important aspect in the development of any scientific theory, is that you test it via experiment to see, does a theory comport with reality? And it's very exciting that some of the most recent experiments that have come out are validating many of these quantum gravitational, what were just hypotheses, like the ER equals EPR holographic correspondence conjecture. The experiments are showing that quantum entanglement, the physical mechanism underlying that seemingly mysterious effect, isn't so mysterious. It's an Einstein-Rosen bridge, traversable wormhole connection. So at this time, we can open it up to take a few questions. I don't have a whole lot of available time, but we'll definitely look at a few questions that might have come up while we were reviewing these experiments and the theoretical development of the quantum vacuum. I'll just go from the top of the list down on my side of things. So Trevor, you're at the top of the list for me here. If you can unmute, we'd love to hear from you.
Yeah. G'day, how's it going? Calling from Tasmania in Australia, so excuse the amazing hair first thing in the morning. But if I understand you correctly,
you're calling us from the future. It's Thursday. Yes. Where you're at.
Absolutely.
Wow.
So I always like that as a perspective check, you know. But if I understand you correctly, if we back up a little bit, going back to the overlaid graphene sheet part that we were talking about back there, that's talking about the Casimir effect on a much smaller scale. So when we're talking about the Casimir effect through the scale relations, as we get lower and lower into the different fields, how does that sort of play out on the smallest scales that we're aware of? I might be going right into new paper sort of stuff, but it came to mind where I was contemplating how or if two spherical units, playing spherical units, might be creating Casimir effect as they brush up against each other under some circumstances. In fact, that was kind of how I viewed the Hawking radiation, blowing it back out again to the black holes. If you had two black holes next to each other, then that might have a Casimir type of effect. Is that suitable to say?
Yeah. That's a great idea that you've come to on that, because actually the repulsive Casimir force has already been incorporated into calculations regarding the quantum entanglement of the vacuum energy density. So those Planck spherical units or quantum harmonic oscillators, when you look at them in a quantum gravitational model, the entanglement is occurring via wormhole connections. That's that ER equals EPR holographic correspondence conjecture. So like a great report on this. Work that was done on this was by Mark van Ramsdonk. He had a 2014 paper called, I think it was Stitching Together Space-Time with Quantum Entanglement. But so, indeed, when we're considering the Planck spherical units, the Casimir force, the Casimir effect, becomes very salient. It's an important factor to be included, particularly because your Planck spherical units are the termination of a wormhole, the mouth of a wormhole. And so they're also they're myriad connected wormhole pairs, like the Wheeler wormhole. Now, if you're familiar with the kind of normal history of calculations with wormholes, they use the static Schwarzschild condition. So the Schwarzschild equations, which don't include things like spin or charge or magnetism. And under these static wormhole Schwarzschild conditions, the Einstein-Rosen bridges, the wormholes, almost instantly, it's calculated they will collapse almost instantly because of the energetic, the gravitational force produced by the energy of the walls of the wormhole. They pinch off because they attract each other. But when you factor in that Casimir effect and the Casimir force, what has been demonstrated is that with your Planckian wormholes that form the micro wormhole network of space memory, of space-time, there is a ever-present repulsive Casimir force that will hold open the mouth of those wormholes. So actually, when you go to the Planck scale and you're talking about PSUs, the Casimir force is what is enabling this connectivity network and this multiply connected geometry of space-time at that scale, i.e. that intrinsic entanglement that we saw being utilized in the quantum energy teleportation experiment. So that's actually, you're right on track. That's a great insight.
Awesome. Thank you.
One thing though, I would clarify a little bit is that on your Planck spherical units, you were kind of considering them as, okay, if they're interacting, what kind of Casimir forces are you going to have between them? An important consideration.
I was trying to do both. I was trying to do both, but I couldn't see how they were doing it externally. But after taking the course and the big answers, I could see how they were doing it internally through the EBR. But then I was like, okay, hang on, I'm only viewing this from one perspective here. I'm not viewing it from all perspectives. So how does this then extend externally? And that's when I was sort of getting visions of the Casimir effect in some way. So, yeah,
an important consideration, because actually, me and Nassim were just talking with a physicist just yesterday, and we were talking about the Planck spherical units, and the physicist asked about, well, is there any kind of like elastic interaction between the PSUs? Like if they bump into each other, are they going to scatter? You know, because when you're doing particle physics, you know, you can get electrons to scatter off each other. There's an elastic reaction between them. But so an important consideration in terms of like the geometry of the Planck plasma is that those oscillators, they're actually overlapping. So you don't actually have, for one thing, you know, that's what we told this physicist is you don't have an elastic interaction because they're actually overlapping. And so in that case, you also want to have like Casimir repulsive or attractive forces between them. Perhaps though, you could conceptually think of if you were to try to separate them the Casimir force between them would be so strong that they'd like instantly come back together and overlap. So almost like we couldn't get enough energy to separate them because of the Casimir force of the attraction.
It did occur to me, Casimir on the inside of them as they overlap one another, like the flower of life, you know, if that's possible. But I just thought that I was crazy for a second there and didn't say anything. But what?
No, you're right on track.
Cool.
Yeah. It'll be cool in one of these unified physics reviews to look at Mark van Ramstonk's paper and also some of the work that are showing how wormholes don't instantly collapse. That, you know, that's an artifact of the static Schwarzschild solutions, but our universe is not static. You know, things are spinning, things have charge, things have magnetism, things have Casimir force interactions, especially when you're talking about Planckian wormholes and those kind of small scales, small distances.